Deflection of determinate beams by three-moment equation method. In this method, we can only solve deflection. So the concept goes like this. Whenever you consider a beam, let's consider this as a simple beam. You have RA on the left and RB on the right. And upon the application of this loading, it will have a deflection. So for the concept of three-moment equation, we are going to introduce 3 points, like point number 1 to be situated at the leftmost end of the beam, together with point number 3 to be at the rightmost end of the beam, since this is a simple beam. And then we are going to place point number 2 to which deflection is being asked. In this case, we are dividing the beam into 2 parts. On the left side is the L1 or the span number 1, and on the right side is the span number 2. What we're going to do now is copy the loading, considering span number 1 first. Copy the loading, and this will be used. So consider a simple beam for this span. So consider a simply supported span. How to make it? Provide vertical reactions, R1 and R2. This time, you are going to solve for the reactions of R1 and R2 based on the loading. After that, you're going to draw the moment by parts of this span. And this is the illustration, together with the centroid and the area of the moment by parts. And then, with the centroid to the left side, it's going to be labeled as barred A1. And on the right side, from the centroid, it's going to be the barred B1. You do the same thing for the second span, L2. Again, consider a simply supported span, so provide R1 and R2 on both ends of the span. Then again, solve the reactions of R1 and R2 based on the area in this span L2. Next is, you're going to draw the moment by parts of this span. This is the illustration together with the centroid and the area. In this case, we are going to still locate the centroid from the leftmost end of this span and to be labeled as barred A2. And also, from the centroid towards the right side is barred B2. Next, you're going to create a positive bending moment at the ends of each span, meaning on the leftmost end of point number 1, you place M1 in that direction. And in the middle, you have M2. And on the rightmost end, in this direction, then this is M3. Remember, from your strength of materials, this is how we create a positive bending moment. And this is our three-moment equation, which is M1 L1 plus 2 M2 parenthesis L1 plus L2 close parenthesis plus M3 L2 plus 6 area 1 barred A1 over L1 plus 6 area 2 barred B2 over L2, and that is equal to 6 EI open bracket H1 over L1 plus H3 over L2 close bracket. And let us define each element. For M1, M2, and M3, these are the bending moments. For L1, this is the span length of the leftmost or left side. And then L2 is the length of the span number 2. So this is 6 area 1 barred A1 over L1, or the statical moment of an area about point number 1, meaning we're going to get the product of each area under span 1 to be multiplied by the distance from the centroid of respective area about point number 1. And then, this is the second statical moment of an area, or the 6 area 2 barred B2 over L2. And this is going to rotate about point number 3. So, in this case, we're going to get again the product of each area under span number 2 to be multiplied by the distances, or the distance from the centroid of respective area about point number 3. And that is your barred B2. Also, you have the EI, or the flexural rigidity. So next is you have H1, or the vertical distance from point number 2 to point number 1. Also H3 is the vertical distance from point number 2 to point number 3. I hope you have remembered this. Remember point number 1, point number 2, and point number 3. So this is how we quantify the length distances of H1 and also the length H3. Do not forget that M1 and M3 will create a positive bending when points 1 and 3 are measured upward in the direction from point number 2. Also, for different beams, for overhanging beams whose deflection is within the span, like for example this one, and this is the type of bending or the deflection or elastic curve, and we are asked to solve for that deflection. So we're going to place point number 1 on the leftmost end and point number 3 at the interior support, which is at RB. So point number 2 will be placed at which deflection is asked. So this is the first situation whenever there is a deflection being asked within the span for an overhanging beam. Next here is for an overhanging beam whose deflection is at the free end, like this one. This is the elastic curve of the beam, for example. So we're going to place point number 1 on the leftmost end and point number 2 on the interior support, and point number 3 is to be placed where deflection is asked. Also, for the last type of beam is a cantilever beam. Say for example, this is a cantilever beam. All we have to do is, for example, this is the deflection or elastic curve, and this is the deflection being asked. For cantilever beam, by the way, it's always at the free end ang permi i-ask for the deflection. So in this case, we're going to place point number 2 at the fixed support all the time. And then in this diagram or illustration, then point number 3 would be on the right side. How about point number 1? For cantilever beam, we are going to introduce an imaginary span on the left side of point number 2. And at the end of the imaginary span is your point number 1. Meaning, from point 1 to point number 2, which includes the span number 1 or L1, then everything there is imaginary. So therefore, its value is 0. Like M1 is 0, L1 is 0, 6 area 1, BART A1 over L1 is 0, together with H1